Welcome, everyone. Thank you for joining us today. My name is Anita Thompson, and I am the North American Sales Executive for Matific Math. And it is with my great pleasure that I introduce our main speaker today, Professor English. Lyn is a professor of mathematics education and the faculty professor of STEM education at the Queensland University of Technology in Australia. She's also a member of Matific's Academic Board, whose role is to ensure pedagogical excellence of Matific's mathematics activities and also ensure that our resources and our activities are aligned to the most up-to-date and research in education and child development. Without further ado, I'm going to turn you over to Lyn. She has a wonderful presentation prepared for us today.
Good morning, everybody. Well, good evening. It's evening in your time, morning in my time. I'm going to just show you some examples, talk about the importance of problem solving in elementary mathematics. The examples I'm going to show you are the ones that I've actually implemented in classrooms. The first slide is just a photo of my city. I'm from Brisbane, which is on the east coast, the middle east coast of Australia, and that's one of my favourite bridges. I do love bridges because they combine all of the STEM disciplines. It's called the Kurilpa Bridge, and it's got cable stays and masts. Yes. Now, I just thought I would have a look at mathematics and the importance of mathematics that we tend to overlook. Now, we've just had an awful year last year and still continuing this year, and from the COVID. But the one interesting thing about COVID is that innovations have come about because we've been faced with problems that we haven't got a clue how to solve initially. And so we have to be innovative. And a lot of these innovations, we've got STEM that's underlying it. We hear a fair bit about the importance of STEM in the vaccine development and also in modelling, which I'll come to in a minute. And complex problem solving has been crucial and continues to be crucial. So we've had a real push in the importance of preparing our students for coping with unexpected problem situations. So that's why I'm trying to focus on today is how we can extend students' abilities to solve problems. So we've heard a lot about mathematical modelling around the world, and they've used mathematical modelling to say how, social distancing, how far apart should we stand? How should we quarantine people? Do we quarantine the whole city or the whole state? Do we need to close events, schools, and so on? And so mathematical modelling has been very important in the COVID, but unfortunately, when they first used mathematical modelling at the beginning of last year, we didn't know the full facts. We didn't know all the variables. And so in Australia, we had claims like Australia will have a ridiculous number of deaths. And so there was panic. And the hospitals, didn't think they'd have enough ventilators and so on. And as COVID went on, the aim was to flatten the curve. And you can see there that the number of cases, when you first start, you have a high number of cases and they're worried about the healthcare system. But as time goes on, you have some innovations that have helped reduce it, but also you've got a greater number of people that have sort of had it and have also got the immunity. But in Australia anyway, there's been a big thing about flattening the curve, but our government has decided that they just don't want to flatten the curve, they want to remove it. So the mathematics has been very important in COVID. But mathematics is important in a lot of our innovations, but we don't hear about maths. And that's why I'm trying to emphasise the importance of mathematics within STEM. And just as one example, I read a little article recently about the Tesla engineer who redesigned the chocolate chip cookie. And he used a particular new chocolate chip that's flat and square with a combination of thin and thick edges. The reason he did that, well, there are two reasons, was that A, It was attractive, unusual shape. Well, I don't know how many people, when they eat a chocolate chip cookie, they actually look at the shapes. But apparently it was also lovely on your tongue, and the taste, the shape of it made the taste really stand out. So that's just a simple example of mathematics that gets hidden in today's innovations. So looking at mathematics in our STEM world, I love Mike Shaughnessy's work. He was the president of NCTM, I think, a number of years ago, and he wrote a commentary, an article in Teaching Children Mathematics, when we used to have that, and he said STEM education must involve significant mathematics, otherwise the end remains silent. And I feel that over the years, STEM has been overtaken by science, engineering has been left out, and so has maths. And I liked Shaughnessy's definition of STEM perspective for a maths education. And he argues that STEM education refers to solving problems where you draw on concepts and procedures from maths and science, as we've seen in the COVID examples, but also the importance of teamwork and design. And I'll be focusing on design in problem solving in the examples that I show you. So I very much like Mike Shaughnessy's work, and the articles that he has, I've got the reference there, well worthwhile reading. Now, mathematical knowledge is very important. We just can't get away from the basic content. And that's what I want to emphasise. But also, basic content is not enough. In our current rapidly moving world, we need design and design processes. And that's actually in the next generation science standards, where the engineering is featured in engineering design with links to other disciplines. We need to be creative and, most importantly, flexible and adaptive. And I think we've all become very adaptive in the last 12 months with COVID. We have to be critical thinkers. We're presented with graphs, maths graphs and data, and we just can't accept them as they are. We've got to look and think critically about the data. We just can't accept everything that, for example, politicians might say. We've got to think critically about the data. And, of course, we have to deal with complexity, complex problems. These other skills are also important, and I believe that we can try and build these skills into the mathematical problems that we develop for children. Systems thinking. Now, that's extremely important today, always has been, but systems thinking is looking at a whole system. But when you start to when you start to adjust parts of the system, they're all sort of interacting and affect other parts. For example, we closed down the international travel in Australia anyway. And so there you've got your airline companies. Look at the impact. You've got the airport employees, the pilots lost their jobs. Other businesses have also suffered, travel agents. So when you affect a system that has many parts, that reverberates. And so systems thinking is important to bring in. Entrepreneurial skills, increasingly important. And, of course, communication and collaboration have always been very important. Now, I've been focusing a lot on design thinking in STEM problem solving because design cuts right across STEM, including mathematics. And just this is just a very simple example of poor design. Now, you've probably seen all these parking signs. I know when I'm in our city, sometimes you see these signs and you think, oh, my goodness, can I park here or not? Well, that's just a pretty probably far out example. But as you can see, this is a much clearer, simpler example, and it does involve mathematical representations, and you can see the design there. You can clearly see when you can park, when you can't park, how long you can park for. And this was actually, I think, a lady designed this a number of years ago to try and improve some of the parking signs. So design is extremely important in today, and you'll probably come across engineering design processes, particularly in your next generation science standards. You will see those engineering design processes which are applied to engineering, but I apply it across in mathematical problem solving as well, because you think about it, you've got a problem, you've got to identify what is our problem. Let's do a bit of research and brainstorm. Let's construct our solution, whatever form might take. But importantly, let's test it. We just can't accept the first solution we get. So let's test it. Now we can improve it. And then we might have to go back to the problem. Let's rethink the problem, and so on. And then you've developed your solution, and you present the solution. So I just digress a little bit, because I have brought in engineering in my STEM and mathematical problem solving. Engineering is important because it helps the students appreciate how everything that we look at and use, even my chair, is designed and engineered. And from my work in engineering in schools, I found that it really helps the students contextualise their mathematics and their science learning. Also, I've also found that it improves their achievement, their motivation. Like when I was in implement engineering in one girls' school, they loved it, and they said at the end, because the teacher was very enthusiastic, and she used to dress up as, for example, if we were looking at a day of, for example, simple one, bridge building, whatever, and she would dress up as an engineer and for the day. So we would have a whole engineering day, and the students would apply their maths learning and their science learning to solving this problem. And really, engineering design, as I showed you in the diagram before, really links those STEM disciplines. So now going on to, folks, back onto mathematics and problem solving. What I've tried to do over many, many years, and my work in modelling with Dick Lesh and so on, and as you can tell, I've been around the ridges for several decades, and so I've been working in schools with problems. And the one aspect that has concerned me is that I want all students to feel a sense of achievement in their problem solving. I don't want just, the so-called brighter children, the ones who might do well on maths, to zoom ahead, and the other students not to. So I always take into account a range of student abilities, and I try and develop problems which can encourage all students to participate. And I refer to that as learning innovation, in the sense that I like problems where students have to generate their own knowledge, their own learning. That doesn't mean to say they learn everything that way, but there are some problems involving mathematics and science and other problems where they actually learn as they go along. For example, in some of my maths problems involving data, students have not been taught mean or median, but my goodness, when they work through the problems, they actually come across and they work out, the meaning of mean and so on. But I think the mathematics and encouraging innovative learners, we have to prepare our students to be adaptive problem solving in this day and age. They have to entertain disruption, which we've all had to in the last year, exceptionally important. They have to be able to tackle new and unexpected situations. Now, if we just stick to basic problem solving, I'm not knocking the importance of word problem solving and operations and numbers. That's essential. Students have to be able to do that. But you're not always going to get those examples in the real world. So we want to expose our students to new and unexpected situations. And also another thing is to see the novel in the ordinary. And as I'll mention again later on, those students who don't do extremely well on all the testing we do, they're amazing with their novel ideas and their novel solutions that they come up with. So what I try to do is, that's just a simple diagram where you've got your maths and your STEM skills and knowledge and competencies on your x-axis. On your y-axis, you've got what I've called learning innovation, being able to learn and adapt as you solve the problem. And if students are just on the basic problems, they remain routine problem solvers. They can do the basic sort of problems. But you come across problems that we don't know, we haven't met before. We want them to be adaptive problem solvers. And so I look at an optimal adaptability corridor. In other words, if we create problems so all students can enter the problems and strive towards a solution, they learn to become adaptive in their problem solving. And you've probably seen this over many years, this reference to low floors, high ceilings and wide walls. And I like this idea because low floors means all students can enter. High ceiling means that the problem is sufficiently open and sufficiently comprehensive that students can excel, can move forward as far as they're able to. Wide walls means that this term refers to being able to share and communicate. I mean, look what I have achieved. And children get really surprised if they've learned something, if they've discovered something themselves. So now I thought I would show you some problems that I've implemented. I've got K to 5 here. These problems I have mainly implemented in, say, grades 2, 3, which are 8-year-olds, through to middle school. But the ones that I'm showing you today have been implemented in 3rd grades, 4th and 5th grade. When I've developed these problems, I've tried to work in with a teacher's curriculum. This is very important because when I work in classrooms with teachers and students, I don't want to be seen as the academic coming in and implementing something else, got something else to teach. So I always try and fit in with their curriculum. Problems that I've got to show you, I probably won't get through all of these, but they're on the slides that you can have access to. Fancy feet, mini golf, some probability, which I know you don't introduce till the upper grades, early settlements, and some earthquake building, resistant buildings, which I have not included here. The first one I've called fancy feet. What we tried to do in this one was look at, there was 2 parts. We brought in mathematics and engineering and science and even technology. So this was a story about fancy feet. We had 2 parts. The first part involved statistics, measuring. So students took measurements of their feet, their what shoe sizes, what are the purpose of the shoes they were wearing. Some children had their sports shoes on or whatever. Popularity or fashion trends. And to link in with their science, we looked at material use because the students had studied different materials. And what's the function of the material? If you're going to make waterproof shoes, you've got to take into account the appropriate features of the materials. So when they investigated the feet, they were involved in posing statistical questions. For example, I wonder what's the most popular shoe size? Who has the longest foot? Or so on. They collected the data in their class or across all of the classes in a grade. They analysed the data, looked at, they collected what was they looked at most popular. They then represented, which is very important. I'll come back to that, but representing their data in a way that they would like to represent it. We didn't say to them, okay, draw a bar graph. or draw a line graph or whatever, we let them choose, and you'd be amazed at the representation students come up with. I've had grade 1 students who'll come up and draw a Venn diagram. They've never been introduced to a Venn diagram. Or a grade 1 student doing a line graph. And they call that a heart monitor graph because they'd seen the heart monitor when visiting somebody in hospital. So they analyse and represent, and then they communicate. They shared their findings in our class. We found the most popular shoe size was what? We found the most popular shoe materials, or the purpose of the shoes was such and such. Now, we also made this as real world as possible. So we explored shoe design and manufacture. Now, I have got a video. I'll only show part of the video.
I've got secrets in my heart. He's got
I'm Jodie Fox, and I'm one of the co-founders of Shoes of Prey. We're a website where you can design your very own perfect shoes. To be honest, I was never really a big shoe lover, and it was mainly because I could never find exactly what I wanted. Either the heel was too low, or it had a bow on it that I didn't like, or it wasn't quite the right colour. So I went travelling, and as I was travelling, in the same way you find someone who can make a tailored suit for you, I found someone I could commission my shoe designs with. So I started to create these shoes, and as my shoe collection became more extraordinary, my girlfriends asked me to commission shoe designs for them as well. And that's when I kind of realised a lot of women could really enjoy this idea. It's such a good feeling when you put on a pair of shoes and you get a compliment on them, and it's something that you've created yourself. It's just wonderful for me. I absolutely love seeing my customers' designs come in and then seeing the finished product and then getting a photo of them wearing them and looking fantastic.
That was a video we showed, and it goes on and shows what's involved in designing shoes, in measuring, choosing materials and so on. And sadly, the company no longer exists because of financial problems. But it was an excellent video because it also, you could go online, and an extension of this was for the students to look to explore that online website and choose, shoe sizes, design, and so on. So we looked at engineers that are involved in that as well as the designers. And this next task was they had to design their own shoes, which involved measuring, selecting materials, having a goal, and so on. And we wanted them to also draw on their knowledge of the first activity when they looked at shoe sizes, measurements, popular designs, and so on. So we, as part of the shoe design, we brought in materials. They had to buy some materials to create their shoes. So we looked at the item, the cost of the item, what was the property of the material, which part of the shoe are you going to put that on, what's the total cost. So they had a budget that they had to adhere to. And they had to select materials that matched their aims, which I'll come to. So the design process here was they sketched their design, chose the materials, measured the materials, cut them out, constructed, and then tested the quality by actually putting the shoe on and finding if the heel didn't work very well. We'll have to do something about that, and they might have to redo it. Yes, and to make this a little bit more demanding for students and to get them more involved, we said, we want you to think of a shoe problem or a goal that your group has identified. Now, some people said, some groups, for example, said, I would really like a good pair of dancing shoes because my dancing shoes are not that good. Or another one said, I'd like a shoe that would be waterproof and so on. So they then had to list 3 aims. Instead of us giving the students the aims of the problem, they had to develop their own aims. How are you going to test how well your design meets your aims? How will you know if it passes the test? So the students developed their aims and so on, and they sketched a range of shoe designs, which I'll show you shortly. And they displayed amazing stylistic features, 2D and 3D perspectives. They showed their measurements and the materials and the functions. So they had to combine all of that into designing their shoes. So testing the first design. What was your problem? What were your aims? And we said, did your design, the measurements and materials enable you to meet your aims? And down the bottom of the slide, you can see some of the shoes they created, which was really, they were amazing. And these were 8-year-olds. And 8 years going on to 9-year-olds. And they were quite surprising. For example, here's one sketch. She thought she would give a face to the shoe, and the measurements centimetres long, and the sole, I think, non-slip and so on. And there was another one where she had the second design, she had foam, ribbon to make it attractive and so on. She said, well, we improved it by taking away the sponge and replaced it with sheeting, with foam sheeting, and added a ribbon because he wanted that to make it attractive or whatever. Here's another one with a heel. I never thought they'd make a heel, but anyway, they did. And they've got, you know, the measurements there, side view. You can see the spelling is not that marvellous, but that's okay. This one, now this girl who did this, she developed a wedge shoe, which absolutely amazed me, but she got the, you know, triangles, and she wanted to make it taller, to improve it. She wanted to make it taller. She used the sandpaper. You can see her measurements and so on, top view. It was quite amazing. She was the only one that made a wedge shoe. And, you know, this student attended mathematics classes and other classes because she was struggling with mathematics. And but she came up with this design. So, you know, you can't judge a student purely by their test scores. So I was really thrilled with this student because she was able to show her creative side using mathematics and science. And one last one, added blue ribbon, added support and so on. But you can see what the students, and we didn't give them any directions. They had to come up with the designs themselves. And it never ceases to amaze me how creative students are. And okay, I'll go on, just watching the time. I'll go on to the next one. The next one was mini golf. I developed this one, and it involved reinforcing area and perimeter of squares and rectangles. Now, this was year 4. I think it was year 4. Yes, 9-year-olds. And 9, probably turning 10. But the teacher had just introduced area and perimeter of squares and rectangles. That's all she'd focused on. So she said, now I would like you to, any activity you develop, could you see if you can reinforce or develop the students' understanding of that? So we thought, well, we'll look at mini golf, and I'm sure you have, I know you have mini golf in the US because I've had a look, and sometimes they're called putt-putt golf here. And what we did was we introduced, the students had a mini golf putt-putt in their local community, and we asked them to have a look at, if they haven't already been there, to at least have a look and see how the mini golf course was laid out. Then we also had a short history of mini golf, and it goes right, or putt-putt or whatever, goes right back 200 years ago, and there was a ladies' putting club in St Andrews was created, and it was the first known putting club in history. So we talked about the history, and we said how the first ones were pretty primitive, but of course we know what they're like today. And here's another one, 1960, I think 1916, there was a Lilliputian golf course, and that was in the US, I believe. and you can see all the different shapes and so on there. They're not just rectangles and squares, obviously, but and that was in New York. They had mini golfs on top of roofs of buildings, and that concept took off, and lots of tops of buildings had mini golf courses start to take shape, which is a great idea. I mean, it's great relaxation, great, you know, interest, community involvement. So the students got very interested in that. So after exploring mini golf courses and discussing materials and shapes and everything, we set them about designing your own mini golf course. But of course, we were limited in the shapes we could use. We said, now we'd like you to create a theme for your mini golf course. And some, for example, created a beach theme or an Australian theme or a scary theme. And they had to determine 3 criteria for design of your mini golf course. You have to think about what do they want their golf course to look like, or to what criteria. And we said they had to use 8 shapes, and we gave them a centimetre squared paper. We said 2 of your final 8 shapes are to consist just of a square and a rectangle. The remaining shapes will consist of combinations of squares and rectangles. So we didn't want them to bring in circles, certainly not at this stage. So they had to have combinations of squares and rectangles. And we said, now for each shape, it's up to you to decide where you would like to place the golf tee and the golf hole. And it said, to make your shapes challenging, we would like you to add an obstacle for each shape. So they had to decide out some obstacle where they're going to place it. And we said your obstacle should fit in with the chosen theme for your mini golf course. And we said you can sketch your shapes, just have a bit of a trial, sketch your shapes first on the centimetre squared paper. And the students, and I didn't include all of these because I didn't have time, the students, they had to design some of their shapes initially. Then through their group discussion, they decided which shapes they would use. And it said, and then afterwards, we asked them several questions which extended their understanding of squares and rectangles and area and perimeter, but also made them think, gave them some challenges to think about. So we wanted them to say, what were your main ideas in creating your mini golf course and the shapes for your mini golf course? How did you decide how to arrange? You had 8 shapes, and we gave them a large sheet of cardboard, coloured cardboard. In hindsight, the cardboard was probably too large. Anyway, I'm just reflecting on how I could have improved it. How did you decide to arrange the 8 shapes on your mini golf course? How did you determine where to place the obstacles on your shape? We also asked the students which of your shapes has the largest area and smallest area. How do you know? How did you determine that? And I've left out lots of the questions we asked, but we wanted the students explained how they determined the perimeter and area. Now, the students had been taught the formula, the procedures, but had just been taught it. Not all students went straight ahead and applied a rule. No, some counted the squares to determine the area and the perimeter. Others counted how many how many units rather on the length and the width, and so on. So there were a range of approaches the students took to determine the area and the perimeter. And we said, what's the largest area and the smallest area? How do you know? And so on. And then in the course of discussion, the students noticed that somebody had a shape where the perimeter was the same as the perimeter measurement ended up being the same number as the perimeter. So that we then explored if your shape has a particular perimeter, well, shapes have the same perimeter, well, they have the same area. So that led off to different discussions and explorations that we had. How did you position your shape on the mini golf course? Why? Does your mini golf course meet your criteria going back to it? If not, which criteria that you wanted to meet didn't you meet? How would you rate your group's mini golf course design and why? And then we said, what changes would you make to improve your golf course and why? And we also like to ask the students, how were you using your mathematics, the mathematics that you know, or the mathematics that you discovered to design your course? And what science? Were you using any science to design your mini golf course? And I've just got two examples of here's one example, but you can see they've sort of spread it out. Had I made that sheet of cardboard a bit smaller, it would have been possibly better. So you can see they've added some obstacles, and they love talking about the obstacles. So that was Australia, that theme. This one was Candyland, and so on. Okay. Okay, now I've got a couple left. I'm going to show you one. This was one we did with 8-year-olds. Now, I know in the Common Core State Standards, probability is not introduced until I think around about grade 6, which is a pity really, because probability is with us everywhere. And these activities were very, very simple introduction to, because you can see, you know, bingo when you, you can see the probability coming up here, and oftentimes we have misguided views of what our chances are. And we start off by playing a simple game of bingo. Now, I know bingo is not legal in some parts of the US. We weren't trading money. We were just simply using counters and seeing who was the winner in that. And we got the students, we had bingo cards, and we said, what do you notice about the numbers in the rows and columns? And we explained to them how to play the game and who the winner was. So that was a very simple game of bingo. We also wanted to think about the bingo game. Does everybody have an equal chance of winning? Why or why not? Was it certain that someone would win? So you've got these basic ideas of a probability, equal chance, certain, possible, impossible. Could 2 people win? And we wanted them to understand the notion of order in which the balls, we actually had a little bingo thing where the balls, numbers came out. In what order? So they just came out in a random order. And are some numbers more likely to come out than others? And sometimes students will think, I love the number 7, so anything that's got number 7, it's got a much better chance. We ask, can 95 come out? No, we don't have 95 on there. Do you think the same person will win if we play the game again? Is it possible or not possible? Then we got them, this was it's a problem-solving activity in the sense that we have not given them specific numbers of counters to put in their bag. We've given them the choice of selecting counters. So they each had 36 different coloured counters, and we said you can only select 12 to go in your mystery paper bag. You can select whatever numbers of each colour you like, but there must be at least one of every colour. And the numbers of each colour do not have to be the same. So the students came up with bags of counters that weren't all the same. They had some variations. And we wanted the students to record the number of each counter that you've chosen to go in your mystery bag. So one group might have 4 blue, 2 red, 3 green and 2 yellow or whatever. So that was per group. And then we asked them to, let's make a prediction. if you could pull out just one coloured counter from your group's mystery bag without looking, what colour do you think it would be? And we want to see if they would understand that the proportion of the colours they have there, if that would affect their chances of pulling out a particular colour. And we said, record the colour that you predict would come out. Now, if a student's just like, for example, love red counters, and it doesn't matter if there's only one red counter there, I'm sure red's going to come out. So we want them to realise that looking at the proportion, the number of red counters and so on compared to the other counters, will affect their chances. So we got the students to record their names, what they predicted, and their outcome. So we got the students to put the counters in, select a counter without looking, and record the colour of the counter, that table I just showed you, and return the counter in the bag and keep on going until everybody's had a go. And we also wanted to reinforce the notion of chance. Does each counter have an equal chance of being selected according to the counters you put in your bag? Is there a coloured counter that has the greatest chance, the least chance? Could you select a purple counter? Is it possible to select a purple counter? No, we didn't have any purple counters. But those very basic understandings of chance, young children come across, we all come across in the everyday world. And I'm just bringing in simple fractions here because this Year 3 teacher, she had introduced fractions earlier in the year, and the students had been introduced elementary understanding of fractions. To introduce or to reinforce a notion of fractions but related to the counters, we got the students to understand that if you, for example, if you've got 4 green counters in 12 counters, you've got 4 chances out of 12 chances of selecting green, or 2 chances out of 12 chances of selecting blue. And then we got them to use coloured pencils to mark on the line which was least likely and most likely to come out. And then we gave them the problem. If you can add 4 extra counters, list the colour counters that you would like to add to the bag. How would your chances change then? So if you now have 3 counters, 3 green counters, what are its chances? And we also asked the students to represent their chances using any representation they like. Now, this was quite surprising because the students had not linked their chances and their fractions representing the chances as a representation before. And as usual, we didn't tell them exactly what to do. They had access to square paper, to plain paper, and to any other paper they might like. We asked them to, what type of representation did you create? Which representation do you think tells your chance story better? Well, here's one representation. And the teacher was amazed. She said, I had no idea. I've just touched on fractions earlier in the year. And she said, I had no idea they would be able to do that. And so a rewarding part of designing these and implementing them in the classroom is the teachers get a surprise as well as the children. So we've got Millicent's representation, and she took a centimetre squared paper, and you can see that she's shown the chances of each coloured counters there, but then she's got the total number of counters on up on the y-axis on the right-hand side. So she's shown the total as well as the fractions. And one other decided he or she would do a pie graph. So you can see what they can come up with, and they really hadn't been introduced formally to pie graphs. But children see the graphs everywhere. They see it on the media. They see it, advertisements or whatever. So they're pretty smart little kids. Look, this is just one activity. I've done this a couple of times, and this fitted in with the history of Australia, where the students were exploring the early settlements in Australia and the explorers and so on, and determining which, for example, this is Queensland. They were exploring, which is my state. Which of the settlements are we going to make the capital of Queensland? And there were various choices, and the students had to look at the early data and decide on which city do you think, which town or place do you think would be most appropriate for the capital of Queensland? They were going to put in Brisbane, which is obviously the capital, but there were other options. And we said, now we'd like you to come up with a system or a model which you can use to decide which particular site in Queensland would be the best choice for a capital of Queensland. And we said, many more ships are going to come to Queensland and they're going to settle in Queensland. We would like your model to be useful to them. How can you help them choose a place to settle? Now, we gave the students, I don't know how well you can see this, but this is a set of data. Now, students can always find this data themselves, but in this case, we gave them the data, and we had 4 options: Brisbane town, Limestone, which is north of Brisbane, now called Ipswich, Rockhampton, which is up on the coast of Queensland, and Toowoomba, which is inland towards the west of Brisbane. We gave them a mixture of qualitative and quantitative data. For example, what access to sea, what land was available for livestock, what transport do you think you could use? Was there fresh water? What was the temperature range? And these are in degrees Celsius, not Fahrenheit. What's the average temperature? How much rain? What resources are available? What about natural disasters? And like you guys up there have terrible bushfires and other natural disasters. So they had to use that data to choose the settlement. And I haven't included examples because time is limiting. But it's amazing that children came up with a number of solutions, and they also applied. They used mean and median, and they had not been taught that. And that often happens. Okay, it's come to my conclusion now. I apologise for going overboard. My argument, my claim all of these years has been, I think we need to capitalise on young students' talents. How can we make today's problem solving more appropriate for today's current problem solving for today's world? And how can we adapt the existing problem solving experiences so we can cater for all children? We want all children to achieve. They mightn't all achieve, say, at a certain level that we might, that some other children might achieve at. And it varies from problem to problem. Some children will go way ahead with a problem and do better than other students. So I'm very concerned about all students being catered for, and how can we incorporate more STEM topics, and there's STEM-enriched modelling, and also computational thinking and technology, which is becoming increasingly important. And I will finish. Oh, that's my website. If you'd like to, I've developed booklets for teachers, booklets that have teaching notes, background information, and student workbooks on various problems that we've curated and we've implemented in school. So you can download those from my website. Okay, they're a bit geared towards Australia, but you can put up for that and perhaps adjust it for the US. Okay, I'll finish here. That's a Sydney Harbour Bridge. which is the town, the city rather, that's often featured in Australia. Thank you, everybody, for listening. Thank you.